So welcome everyone to today's RAW webinar. It's my pleasure to introduce today's speaker, my colleague Christina Imdahl. So Christina is an assistant professor of machine learning and operation management at Eindhoven University of Technology. She got her PhD from KLU, so the Kuna Logistic University in Hamburg, and her research is focused on decision making and operation management and combination of a stochastic and robust optimization with empirical analysis to gain insight into the performance. So without further ado, I want to give the screen and mic to Christina. So Christina.
Yeah. Thanks, Reza. Thanks for the introduction, and thanks also for inviting me. I'm very happy to give the first seminar of the first RAW seminar of 24. My research is on a rather application-based project. So we are applying robust optimization to a capacitated inventory management problem, where you have a capacity, but you can also extend this capacity at paying an extra cost. So we're rather using things that we already know about robust optimization and applying that in that inventory management context to gain insights into the policy and into good decision making for that problem. So to give you a bit of context, what we look at when we talk about capacitated inventory management problems and why it is important, you can think about having a labor force. So you typically have a fixed number of employees that you can use in your work scheduling. But sometimes during peak times, you may want to use more labor. And for that, you could employ temporary workers. But for those, you would need to pay an extra amount because you also would need to pay to the temporary work company. You could also think about manufacturing, where you have a pool of machines. All these machines have a certain capacity. And if you need to produce more, then you need to work overtime or extend the shifts, which also often comes at an overtime premium. And lastly, also in transport, you often have a dedicated amount of trucks that you can use for your fleet management and for your transport management. And if you need to ship more, then you need to go on the spot market and need to see whether you can find a transport unit there, which also often comes at a higher price than in the pre-negotiated price for the dedicated fleet. And the last one is indeed a setting that we mostly look at. So as you may have heard about, in the last years, there has been a shortage of truck drivers. So for example, in 2022, the shipping costs increased between 20% to 100%, as it was increasingly difficult to find truck drivers to do the transportation routes. And we were working with a fast-moving consumer goods manufacturer, and they were using a third-party logistics provider to transport the items they were producing at their manufactories to the customers and warehouses. And with this dedicated, with this third-party logistics provider, they had a dedicated capacity for each period that they would know upfront. And if they want to extend that capacity, they would have needed to go to the spot market where they could get additional transport units, but they need to pay an additional fee rather than the fee they pay to the third-party logistics provider. So we model this as a backlogging system with a piecewise linear sourcing cost. So unmet demand is backlogged. That means that whenever we cannot fulfill a demand in the current period, then we can fulfill it in the next period. That means we have a rather typical inventory evolution. So the inventory of the current period is the inventory of the previous period, plus the orders that we placed in the morning of the current day, minus the demand that occurred during the day. So we also look at the lead time of 0 here in this setting. For this, we adopt a piecewise linear sourcing cost. So the costs that we formulate consist of the inventory costs, so that are inventory holding costs and inventory back order costs per unit, so B costs per unit. And then in addition to that, we have a standard transportation fee that we need to pay for every unit that we source below the capacity. And then we need to pay the standard fee plus a cost premium for every unit that we source above the capacity. We assume that in our setting also that the holding costs are smaller than this cost premium and are smaller than the back order costs. So that means it is cheaper to hold additional inventory than to extend the capacity, but it's also more expensive to backlog than to extend the capacity. So in this setting, compared to the linear system or to the uncapacitated system where we don't have the capacity constraint, we have two key trade-offs. So if in times we have low capacity and a high demand, like in this period, then we can postpone the demand. For that, we would incur backlog costs, but we would save the spot premium. On the other hand, we could advance orders. So then we would also reduce the spot premium, the future spot premium, but we would increase the holding period for that period that we advance it to. And this inventory problem is not new. So we know that for this problem, the stochastic optimal policy has a generalized base stock policy structure. That means that the stochastic optimum policy has two base stock levels, a high base stock level, S1, and a low base stock level, S2. And the policy says that we order up to S1 if we have high inventory. So if we're in this region, then we order up to S1. If we would need to order more than the capacity to order up to S1, then we for some time only order exactly K units. And then if we are still below the lower base stock level when we order K units, then we go beyond the capacity and order up to S2. So we have three regions on how much we order. We first order exactly up to S1, then we order the capacity, and then we go beyond the capacity and order up to the second base stock level. This policy essentially smoothes the ordering process. So in this period, we order less than we actually would like to avoid the cost premium that we would need to pay for the extra units. So problem solved. We know what the stochastic optimal policy is. Well, we don't know the full policy. We know what the policy structure is, but we don't know how to obtain the base stock levels. So far, we can only obtain those base stock levels numerically. And this is typically difficult because we may have limited history demand history to estimate the demand distribution, or demand is non-stationary and intermittent, making the numerical derivation of the base stock levels difficult. In addition, we would also like to generate some insights for the company to understand when do we actually want to advance or postpone orders to avoid the spot premium, and what can we learn from that. And this is so far not possible with mainly computational derived base stock levels. So we use robust optimization to which can partially alleviate some of these challenges that I just mentioned, especially on the non-stationary demand. We build up on theory that I think many of you know. So we mainly build up on the paper from Mamani, Naziri, and Wagner, who solved the uncapacitated problem. So solve the problem when there is no capacity constraint, and show what is the robustly optimal policy for that uncapacitated problem. For that, they use the CLT, so the central limit theorem formulation of the uncertainty set that has been developed by Bundy and Betsimas. And We also employ the idea of the budget of uncertainty that has been introduced by Betsimas and Ziem in this Price of Robustness paper. So we build on some theory that has already been there and apply it to our setting. So why do we use robust optimization? Well, first, in our setting, it provides tractability, so we can formulate the worst case demand, and by that we can derive closed form solutions for the robustly optimal base stock levels. Second, the policy that we derive, the robustly optimal policy, is interpretable. So it generates insight in exactly when do we want to advance and how much do we want to advance. And we also test for the manufacturer that we are working with, how well does this perform in practice, and also in comparison to currently employed heuristics. And we show that actually the robustly optimal policy performs very well in a numerical study, but also when employed to the data of the manufacturer. So first, let's look at the robust formulation and at the solutions to the robust formulation. So first, we formulate the uncertainty set. To formulate the uncertainty set, we use two kind of bounds. So we first have the periodic demand bounds, which basically bound the deviation that the demand can have in each period. We therefore bound it basically by the deviation from the mean demand in terms of standard deviation. And the gamma hat is basically the periodic bound parameter. And then second, we use kind of budget of uncertainty here. So we bound the cumulative demand that can happen. So here the idea is mainly that in each period, the demand can deviate like a lot. But then when we sum up over multiple periods, the likelihood that in each period, the demand deviates very much from the mean demand is less. So you may have a very high demand in one period, but then the likelihood that the next period demand is also very high is reduced. So typically these bounds gamma hat are smaller than the bounds of gamma. Then we can formulate the minimum and maximum demand with respect to that uncertainty set. So the minimum demand is basically the sum over the next n demand realizations, where all of these demand realizations are within this uncertainty set, and the maximum demand is the maximum of the sum of these demands, where all of these demands are still in the uncertainty set. And these formulations are the explicit formulations that have also been derived by Mamani et al. So here we can formulate these, we can explicitly express these formulations in terms of the gamma parameters and the standard deviations. So now we formulate the robust optimization problem for our problem. So first, we also employ the rolling horizon formulation that Sanang Famigam employed. So we solve the linear program over a planning horizon, that is capital H. So we look at a horizon from t to t plus h minus 1. And then we find the optimal solutions, but we only employ the order quantity for the current period. So we only implement Qt, the optimal order, robustly optimal order quantity for the current period. Then we observe the demand, and then we solve the next LP. So this is sort of the implementation of a rolling horizon period. Then the robust model is this here. So we minimize the costs, which consist of the standard sourcing costs, C times Q, plus the inventory costs, plus the premium that we need to pay for each unit that we source beyond the capacity. And then we describe the inventory holding costs here. First, the worst case holding costs. So these are the holding costs with respect to the minimum demand, because in that case, we incur the highest holding cost possible. And second, the worst case backlog costs. So this is the back order cost that we incur with respect to the maximum demand possible within our uncertainty set. And then lastly, the premium ordering costs. So for every unit that we source beyond the capacity in that period, we need to pay a cost premium, and that makes up our cost premium costs. So this is an extension of the uncapacitated problem. So the uncapacitated problem is the same formulation, except that the uncapacitated problem doesn't have the constraint set Fn. So these constraints here would not be there in the linear problem. So clearly the solution to the linear problem is also a feasible solution to our capacitated problem. The solution to the linear problem is known from Mamani et al. So they derived that the robustly optimal solution for the linear problem or the uncapacitated problem is given by a cumulative base stock policy. So they formulated the sum of the order quantities would always order up to this base stock level. So in each period, for each period, we sum up all the orders of consecutive periods, and they order up to this cumulatively formulated base stock level. And these here, the Sn hat, is the linear optimal solution. That's the cumulative base stock level that they found for the linear problem. And also Q hat we use to identify the optimal, robustly optimal order quantities for the linear case. As said, the optimal solution to the capacitated system is also a feasible solution for the uncapacitated system. And if we start with that solution, so if we start with that base stock policy that is optimal in the uncapacitated problem, then we can improve the system cost by shifting units. So what we find is that if these constraints H and B are tight, then if we advance units, then we are basically paying a holding cost extra, but we're also saving the cost premium. And if we are postponing orders, then we're paying the back order costs, but we are saving the cost premium. So just to visualize this a bit, here we can see the worst case demand realization and the base stock. We start with the base stock policy that we would generate from the past one. So here in this setting, we can improve the solution by shifting orders from these capacitated periods to an uncapacitated previous period. So if we move, in this case, a unit 1 period ahead, we need to pay H, but we're saving CP. And if we move from the T+2 to T, so if we move 2 units, then we incur an additional cost of 2H, but we are also saving CP units. And as long as 2H is smaller than CP, then we're saving. If 2H is higher than CP, then we would not be saving, and we would pay additionally. And with that lemma, with that shifting idea, we can actually, finally formulate the robustly optimal policy and show that the robustly optimal policy is indeed also a generalized base stock policy. So that is rather nice. We can show that the robustly optimal policy structure is the same as the stochastic optimal policy structure. To do so, we use a kind of simplex algorithm where we iterate over the edges of that convex polytope that's shaped by these 3 condition sets. We start here with the solution to the linear system. And then we use this shifting idea that we formulated in this lemma 1 by shifting orders always from the capacitated period to a non-capacitated period. So by doing that, since H is smaller than CP, smaller than D, we can save by advancing orders. So whenever we advance an order, then we save the cost premium, but we pay H, and the difference is positive. So we're saving if we're advancing orders. And if we do that greedily, so we shift 1 unit, we first shift 1 unit, then we shift 2 units, then we shift 3 units, then it is never optimal to shift a previous unit again, because always shifting 1 period is better than shifting 2 periods. So we do that greedily, and this is just the analytical formulation of this. So if we shift 1 unit and we have capacity, if we shift from period I and we have capacity in that period, then we have at most the capacity, because we're never going to shift to that period above the capacity, or exactly what we can shift from the previous period, from periods M ahead to that period. On the other hand, if we are above the capacity in that period, then we want to look at what can we shift away from that period. So what can we shift to previous periods from the period? And then our capacity is at the minimum K, because we never shift more away from this period than K, or the most that we can ship. And we first, as I said, shift 1 unit, 1 period, 2 periods, and so forth. And by doing that greedily, and due to the convexity of our problem, we can continue until no further improvement is possible and obtain like that the optimal policy. So this is a sneak peek on what the optimal policy is. The optimal policy is a generalized base stock policy again, and the lower base stock of the optimal policy is the same as the base stock level of the incapacitated system, so it's S hat. And the higher base stock level is the base stock level of the incapacitated system, adapted by a shifting need. And that shifting need tells us exactly how much from future periods we want to shift to that current period. So we will never shift more than actually we have shifting need for it. And if current inventory position allows it, we will advance orders up to that shifting need to the current period. So let's formalize these concepts. So the shifting need at time t over a certain horizon S is defined as the sum of all the capacity slacks, the maximum sum of all the future capacity slacks until these periods. So it's maybe easier to show that with an example. Assume we have these orders quantities in the incapacitated system, and we can see that we have in this period 3 units above the capacity, in this period 1 unit above the capacity, and in this period 2 units above the capacity. Then the shifting need for the current period, so for t equal to 1, looks at how many of these future capacity peaks do we want to shift to period 1, taking into account that we can also shift to the preceding periods before we actually reach t equal 1. So that means, for example, t equal 3, we look at, okay, there's still one gap at time 2. So one of these periods can be shifted to time 2, and there's still a need of 2 units to be shifted to period 1. Similar for the peaks in period 5 and 6. We have 3 peaks in total. 2 of them can be shifted to period 4. So there's only 1 left that would be needed to be shifted to period 1. So in this setting, the total shifting need would be 3 units, because after being able to shift to the previous periods, there would be still 3 units left that we would like to shift to period 1. So with that, we formulate the lookahead peak shaving policy. That is the policy that we formulate in this paper. And here we look S periods ahead and look at and formulate a lower base stock level as the optimal base stock level in the linear system, and the second base stock level as the base stock level in the incapacitated system, plus the shifting need over the next S periods. And then the lookahead peak shaving policy has this this generalized base stock policy structure with these two different base stock levels. And then finally, the optimal, robustly optimal policy for this problem is a lookahead peak shaving policy with a lookahead horizon of S being equal to CP divided by H, and then rounded down. The reasoning behind this here is that if we can at most shift S times H periods, after that it is not financially beneficial anymore to shift more periods, because then shifting more periods would be more expensive than incurring the cost premium. So that is why we only want to look CP divided by H periods ahead. So let's look at how this policy would play out. So we look again at our example that we had before. We had the 6 units above the capacity, a shifting need of 3, but now in this first period, there's only one place to shift. So we actually only order 1 unit extra, even though we would like to order 3 units. And the unit that we shift eventually we call the peak shaved quantity in our context. I said we want to derive closed form expressions for the policy. So let me also show you that we did that. We have closed form expressions for the optimal order quantities in a system with linear sourcing costs. And then using those and the expressions that we can derive for the shifting need, we actually can derive closed form expressions for the shifting operator. These expressions don't necessarily look nice. Those expressions are not necessarily easily interpretable. But what it does, or how it also reacts in response to capacity changes, that is easy interpretable. And that's a bit what I want to show you next. So the lookahead peak shaving policy actually modifies a linear system to anticipate future demand. What that means is if you look at this year, just the straight line, that's the linear system. That's everything we would order in a linear system. But then under the capacity constraint, we use low inventories to actually shift, or high inventory levels. We use high inventory levels to actually still use the capacity to shift units from future periods to the current periods. And this is this gray area here. A unit that is ordered as part of this sort of gray area is additionally ordered under the generalized base stock policy in comparison to the optimal policy in the linear setting. And this is what we call the peak shaved quantity. This is how many units of the future periods are we advancing to the current period. So how does the system behave when current capacity is changed? So let us look at this example. We start with a certain inventory level, look at how the order quantities change, given that the current capacity level is changing. So first, when still the capacity is lower than the current order quantity, we don't advance any orders from future periods to the current periods. Then when the capacity increases and we have space in the current period, we advance some items of the future periods, and that also increases exactly by 1. Whenever the capacity increases, then also the amount that we advance changes by 1 unit. But it only does so until, basically until here, this point is reached, and then exactly the shifting need is advanced. So we never advance more than the shifting need, even if the current capacity is ample. And then second, we look at how the system behaves when future capacity is increased. So if future capacity is increased, then this has an impact on the shifting need. Namely, if future capacity increases, then demand that is advanced originally from periods that are even after that period, they are being advanced to only the period where we increase the capacity and not to the current period anymore. So how that looks like is that first we advance if the capacity of that future period I is very low, then we advance a lot of units to the current period. Then we actually, when the capacity increases further, then the how much we advance to the current period decreases, but that decrease stops until basically that period falls out of this equation here. So then that means it stops until no units from that period or any later period are being advanced to the current period. And then we only advance from period t+1 to period I, because basically the capacity of that period I is getting so ample that it can swallow every peak demand that is occurring in the periods after period I. So then we looked at the performance of the system. We actually have 2 systems that we compare to. So once we do a numerical study, and then second, we have a small empirical study this way as well, where we work on data of the manufacturer. So to look at how our lookahead peak shaving policy works in practice, we need to also find some rules how to actually employ that in settings. So we decide that, so typically for every period, we have a bound. We have a period dependent bound, and we have the cumulative demand bound. And they can vary per period, but we set them the same for each period. Essentially, we have 2 bounds, one the cumulative demand bound and one the per period demand bound. So these gammas do not vary per n anymore, but are only 2 parameters. And these 2 parameters we use as tunable parameters, so we in the end have 2 degrees of freedom. When we later come to our empirical study, then we use for future demand, we use the mean demand, we use the forecast for, and we estimate the standard deviation with the forecast error from the past periods. So we actually use a MAPE to estimate the standard deviation of the forecast. And we compare to 2 benchmark policies that we actually also discussed with the fast-moving consumer goods manufacturer. One is the Z-score policy, which basically sets the higher and the lower demand level according to the mean demand plus Z times the standard deviation. And the higher level has 1 Z parameter, and the lower base stock level has 1 Z parameter. So this policy also has 2 tunable parameters, just as our policy as well. And then we compare to the days of sales policy, which is also typically employed in companies to take also a bit the non-stationarity of data into account. And with the days of sales policy, the higher base stock level is set to look M1 days ahead. So we actually use the forecast of the next M days, and that is our base stock level. And the same we do for the lower base stock level, and M2 is then smaller as M1, and also both of them are tunable parameters. So you can see both of the policies, yeah, they counteract one thing, but they don't look at one other thing. So for example, the Z-score policy, they don't take the capacity or the future capacity into account, while the day of sales policy doesn't take the variability into account. They take the non-stationarity into account, but not variability, and also not the capacities. So now in our experiment, we want to figure out when is our policy actually the most valuable, and how does our policy perform in practice in comparison to those two benchmark policies. We look at all the costs here in terms of expected cost performance. So we're not looking at the worst case cost performance, which you can argue is a bit unfair because the robust policy is obtained with respect to the worst case cost. But this is typically what companies are more interested in practice. What is the expected cost performance of the policy? So we first start with some numerical studies, and we have quite some degree of variation in these charts. So on the left-hand side, first we vary the degree of non-stationary. So we have a mean demand of 10 if the degree of non-stationarity is 0. And if the degree of non-stationarity is, for example, 1, then the mean demand varies around 10 with a standard deviation of 1. But still the mean demand is known in advance. We only use that variation in our simulation. So we use this to simulate non-stationarity demand. And the higher the standard deviation, the higher the degree of non-stationarity. So the more this mean is fluctuating throughout the time. And similarly, we also simulate the capacity. So also the capacity fluctuates around the value with a certain standard deviation. And then in the left chart here, we look at the improvement of our policy, of the lookahead peak shaving policy over the Z-score policy. And here to the right, we look at the improvement over the days of sales policy. What we can actually find here to the left is that when the standard deviation of the capacity is 0, then there's no improvement, because then there's no variation in the capacity. So actually the disadvantage of the Z-score is that it doesn't look ahead at the capacity, but if this capacity is fixed and not changing over time, then that doesn't matter. At the same time, just as a comment, our policy is optimal when the degree of non-stationarity is 0. So if we don't have any any variations in the demand, then our policy is actually optimal. We can see here that the improvement of our policy over the Z-score policy is increasing with the variation of the capacity, but it's rather stable if the mean increases. So here the improvement over the Z-score policy is really dependent on whether the capacity fluctuates or not. On the other hand, for the improvement over the days of sales policy, we can see that our policy improves and outperforms the days of sales policy by up to 10%, and that percentage increases if the degree of non-stationarity increases, but also if the standard deviation of the capacity increases. And then second, we look at how does actually correlation also impact our results, and how does the standard deviation impact our results. So at the bottom here is the standard deviation, and the blue line is if we don't have any zero correlation, and then the orange line is if we have negative correlation, and blue is if we have a positive correlation, and we model this within AR1 process. So what we can see here as well is that the more standard deviation we have in the demand, the less we are outperforming the Z-score policy. And in addition, if demand is positively correlated, then even the Z-score policy outperforms our policy. This also makes sense because the benefit that we have of looking ahead and shifting and advancing units from future periods, that's more pronounced when actually we can advance units. So if you have positive correlation, basically the likelihood that you have multiple high demands one after another and multiple low demands one after another is increasing, and then you can advance less orders to the current period. And we see similar effects, but less strong in the days of sales policy. Then lastly, the comparison in the small empirical study that we had. So we looked at the goods of this fast-moving consumer goods manufacturer. We looked at one quartile, so the shipped quantities in one quartile of 2019. Those were around 900 units that were shipped between one plant and warehouse combination in North America. And we used the actuals and the forecast they had to compare the two benchmark policies. And here we can see this is just a summary graph over all the items where we fitted the policies to, and then sorted by size. And we can see that the blue line is basically how we compare to our look-ahead peak shaving policy and what are the costs here. Then we can see that the Z-score policy has a 7% higher costs, and the days of sales policy has a 39% higher costs. So over all those items, we're saving 7 to 39%, depending on the policy that you're using with the look-ahead peak shaving policy. So in summary, the policy that we obtained with robust optimization is tractable and also easy to use in practice. The shifting operator is intuitive and gives you a way to interpret also when and why you are advancing orders. And the policy actually outperforms heuristics that are used in practice by now. So thanks for joining, and I'm here for questions.